Thanks for attending my presentation. It will deal with the effect of heat treatment on the impact toughness and brittle fracture initiation mechanism of a quenched and tempered nuclear pressure vessel steel. So first, why study the impact of heat treatment conditions on such properties on such material? In nuclear power plants, some components, such as the pressure vessel or the steam generator, are made of thick forgings of low alloy steel. So now, how do you obtain those components? You start with an ingot, you have here, and then you forge, there is some forging and heat treatment steps to give the ingots its final dimensions to remove impurities from the material. Then, the quality heat treatments will aim at giving the material its required mechanical properties. It starts with an austenitisation at around 900 degrees during several hours, followed by water quench. During the water quench, since the components are very thick, the thickness usually ranges from 100 mm to 700 mm in the most extreme cases. The cooling rates, there will be gradients of cooling rate. There will be a gradient of cooling rate through the thickness. However, the cooling rates impacts the microstructure that you have. So you have a gradient of microstructure through the thickness. And as a consequence, you have a gradient of mechanical properties through the thickness. Following the water quench, there is a tempering steps to try to homogenize some of the mechanical properties. And we will see that you cannot homogenize every mechanical properties of the components. And then, after some milling steps, we have a component that is ready to be assembled in a nuclear power plant. So, however, as of now, there is no systemic investigation of the relationship between heat treatments, microstructures, and mechanical and fracture properties for a unique material. So that's what I'm going to do in this presentation. So, what is our methodology to study the impact of heat treatment conditions? We start with an homogeneous industrial low alloy steel used in nuclear power plants. You have the typical chemical contents of such steels on the table here. And then we cut 8 plates from the block that you have here that comes from a real part. And we are going to heat treat those 8 plates so as to replicate the heat treatment that happens at different level of thickness. So we start with an austenitization at 808 degrees during 2 hours, followed by the cooling step. So here we consider the most extreme case of a component that is 700 mm thick. So we do 2 cases of cooling. One slow cooling at 150 degrees per hour, which is the cooling rate that you can have in the mid-thickness of the component. And fast cooling at 10,000 degrees per hour, which is the cooling rate that you find at the surface of the component. And since we are studying the impact of heat treatment conditions, we are also going to study the effect of tempering. Here we introduce the tempering parameter. It's a quantity that is used to estimate the intensity of tempering by using both the tempering temperature and the tempering duration. And we are going to consider 4 different tempering conditions, and we explore both the effect of temperature and tempering duration. Here for this study we will just use the tempering parameter. So now if we look at the results, so first for tensile properties. So we have done the tensile testing at 3 different temperatures, but here we will just look at the result at room temperature. So first, the materials seems to share a similar work at an hardening behavior. Ductility remains hardly impacted by the heat treatments, both for the plastic elongation at rupture or the reduction of area at rupture. And the cooling rates increases both the yield strength and the ultimate tensile strength by around 50 MPa, and tempering decreases both yield strength and ultimate tensile strength by the same order of magnitude. So, now that we have seen the most basic properties for material, we can look at the impact toughness properties. So, for each 8 materials, we have done 15 instrumented Sharpie tests. And you have here the ductile to brittle transitions for all those 8 materials. And you can see the significant impact of the cooling rates on the impact toughness properties. Indeed, the fast cool materials are much more tougher than the slow cooled one, with a transition temperature which is approximately 70 degrees lower, and upper shelf energy which is about 70 joule higher. And we see that tempering has an effect on the ductile to brittle transitions, but it's much less significant than the cooling rates. And so your tempering step in the industrial process cannot homogenize your impact toughness properties. This is all the more important that you see this variation of impact toughness properties takes place in the same components. So now we would like to understand, we would like to explain those differences. So in order to do that, we are going to work on for the brittle fracture. So we are conducting a fractographic study of all specimens in the brittle regime. So here our criteria was all specimens below 80 joules. So this corresponds to the area here on the transitions. Both sides of each impact of the toughness specimens have been observed, and a number of characteristics have been studied, such as the number of initiation sites, their position, their nature. We will talk about especially the type of initiation sites. And ADX analysis have been done systematically on all specimens to check if there were an inclusion on the initiation site. So now if we look at the results, so transgranular cleavage was observed in all specimens, all 43 specimens observed. And what is interesting, that all the specimens, whatever the materials, share the same initiation, brittle fracture initiation mechanism. If you look at the picture on the left, you see a facet border here, and there is no macrostructural constituent that is visible. And this is the most common case. Thus, the brittle fracture initiates what is likely to be a macrostructural boundary, but there is nothing that could have caused the rupture. We have also a case when you can see traces of carbides in the very vicinity, but you cannot link the initiation with the carbides. But it always happens at the facet border. And finally, for the picture on the left, you are always at the facet border, but there were some inclusions that braked and caused the initiation of brittle fracture. So to summarize, for all our specimens, so for all the materials considered, cleavage initiation always happens at the facet border, so a microstructural boundary, with sometimes some constituents that could maybe modify the behavior, but those constituents does not seem to be necessary to the initiation of brittle fracture. We can also have a look at the distribution of the types of initiation regarding the impact test parameters. So if you take a look at the initiation on facet border with inclusion, you see that they are mostly localized at low energy configuration. You have some rare cases where it happens at higher energy, but it's always for the material with the less intense tempering, so with a higher yield strength. For the initiation on boundary only, or with the presence of carbides, it happens on all the range of energy and temperature. So we have a very different impact toughness behavior from between the materials. Yet we have the same initiation mechanism for all materials. So we try to estimate the critical fracture stress. So it's based on the load diagram method by Shawati. So using the sharply instrumented curve, you can derive, so it's an estimation of course, the critical fracture stress for brittle fracture. And you have the results on the graph here, and we found approximately the same thing as the ductile to brittle transition. The cooling rates increases the critical stress, so it increases the impact toughness properties, and the temperings tend to decrease the critical stress, so have a negative impact on the impact toughness properties. So to summarize, in this study, we have explored the effect of treatment conditions on mechanical property, both for tensile properties and impact toughness properties. the higher the tensile strength, the higher the impact toughness of the material. For all materials considered, the initiation mechanism is the same across all microstructures, with the facet boundary being the key elements in the initiation of cleavage. Some secondary phase can have an impact on the initiation, but it remains to be investigated. Sorry. And also, we estimated the critical cleavage stress for cleavage based on the impact test instrumented curve, and it roughly correlates with the transitions, the different transitions that you observed. So for future work, the critical stress will need to be evaluated experimentally to validate the estimation that we had from the impact test. The facet boundaries that we observed will also need to be completely characterized across all microstructures to see if there were any differences that would explain the difference in impact toughness properties. And finally, this results so that some hypotheses of local approach modeling of brittle fracture, which is usually initiation on brittle particle that fracture at the beginning of, at the onset of plastic deformations, could be maybe improved. And thank you for your attention.
Okay, thank you.